Welcome back to today's Explainer. We are diving into a literal detective story at the atomic level. Today, we're unlocking the Zeeman effect. It's this absolutely fascinating scientific journey that connects the invisible, tiny quantum world directly to the macroscopic forces of magnetism. So, let's jump right in and break down exactly how this works. Now, let's start with a pretty fundamental question. Can a magnetic field actually affect the light emitted by atoms? Think about it. The logic here is really tantalizing. Because if electrons are charged particles in motion, a strong magnetic field should, theoretically, influence that motion. And if you change how they move, wouldn't that alter the very light those atoms give off? It's a brilliant question. But answering it? Well, that requires some incredibly precise observation.
To actually test this, we can't just rely on math or theory on a whiteboard. We have to build something physical. And this setup perfectly illustrates how physicists bring invisible forces into the tangible world. What we're looking at here is a complete optical rail lab experiment. You've got this complex, wide array of lenses, power supplies, and mounts, all stretched along a long black track. We're literally going to use this gear to force atoms to spill their secrets under the intense pressure of magnetism.
Okay, let's dive into this specific apparatus and see how the whole shebang fits together. Right in the middle there, you'll see a small, glowing white tube. That is a cadmium gas lamp, or seed lamp for short. Notice how it's just squeezed right between those two massive, heavy copper coils? Those are the poles of a seriously powerful electromagnet. The light from that trapped cadmium lamp shines straight down the rail, passes through a polarizer and a wave plate, travels all the way through a long telescope equipped with a dial gauge, and finally hits a digital CCD camera on the far right side. That camera is crucial because it lets us capture exactly what happens to the light when we flip the switch and power up those massive magnets.
So how does this actually play out on the lab bench? Let's walk through the steps. First off, we turn on the cadmium gas lamp, and it emits its own signature spectral lines. Step 2. If we look through the telescope right now, with zero magnetic field applied, each energy transition just looks like a standard, pure, solitary band of color. Simple enough, right? But step 3 is where the magic happens. We power up those massive copper coils, throwing a huge magnetic field directly across the lamp. This intense field actually shifts the internal energy levels of the electrons deep inside the atoms. And finally, step 4. As a direct result of those tiny microscopic shifts, that single solitary spectral line suddenly splits into multiple distinct lines. This right here is our big eureka reveal. When you compare the camera captures side by side, the difference is absolutely undeniable. On the left, where B equals 0, meaning, the magnets are off, the emission spectrum shows just one distinct, single green spectral line. But look over on the right. When B is not equal to 0, when that strong magnetic field is pumping, that single line violently fractures into multiple, tightly packed lines. Just imagine how shocking that must have been to see for the very first time. By literally just turning on a magnet, a pure color emitted by an atom physically breaks apart into pieces.
So this wild visual phenomenon actually has a name, the Zeeman effect. Simply put, it's the splitting of one spectral line into multiple lines when a strong magnetic field is applied. This is our solid, memorable anchor for everything we've just seen on the bench. The magnetic field is fundamentally altering how these atoms emit light, taking a single solitary wavelength and pulling it apart into several nearby wavelengths. It is a perfect observable demonstration of invisible forces manipulating atomic structure.
But why exactly does this happen? To really wrap our heads around the mechanics, we've got to shift our focus from the heavy lab equipment down to the microscopic physics of the atom itself. It all boils down to the fact that a moving electron behaves exactly like a tiny magnet. And because they act like tiny magnets, when you drop them inside a giant external magnetic field, like the one from our electromagnets, they are literally forced into different orientations. Those different orientations end up having slightly different energy levels. And as we know in physics, a difference in energy directly causes photons of slightly different frequencies to be emitted. So instead of getting one single wavelength, several nearby wavelengths are created and then captured by our camera. Now, what's really interesting about this energy level diagram is how beautifully it maps out that exact quantum leap. Let's trace it out together. On the left, with no magnetic field, an electron drops from a higher energy level down to a lower one. It releases a photon, which is represented by that single green downward arrow labeled F0. That gives us our original single spectral line. But look over on the right. Under the heavy influence of the magnetic field, that upper energy level actually splits into 3 distinct orientations, labeled ML equals 1, 0, and -1. Because their starting heights are now slightly shifted, the drops down to the bottom level represent 3 different amounts of energy. Those red, green, and blue arrows highlight these new energy differences, which correspond to the F0 minus FB, the original F0, and the F0 plus FB frequencies at the bottom. One single energy state has perfectly split into 3 distinct frequencies of light right before our eyes.
We really can't talk about this incredible phenomenon without putting a human face to the discovery. This is the physicist Peter Zeeman. It was his groundbreaking work that first observed this exact splitting of spectral lines. By proving that magnetic fields interact directly with the internal workings of atoms, Zeeman provided absolutely crucial evidence of how charged particles behave on a microscopic level. His meticulous lab work fundamentally transformed our understanding of atomic structure, cementing his name forever in physics history with the namesake effect we're exploring today. So, we've spent our time today looking at how this works on a lab bench using a simple cadmium lamp and some copper coils. But I want to leave you with a final, really provocative thought. If this microscopic splitting happens in a small lab, how could these tiny atomic shifts help us measure the massive magnetic fields of distant fiery stars? Just think about the sheer scale of that for a second. By attaching spectrometers to our most powerful telescopes and hunting for this exact same Zeeman splitting in the starlight reaching Earth, astrophysicists can actually map intense magnetic storms on the surface of our sun. They can even measure the magnetic fields of galaxies light years away. The very same physics principle that splits a tiny beam of light on a desk in a university lab is literally the ultimate key to unlocking the magnetic secrets of the entire universe. It just goes to show how foundational physics connects the incredibly microscopic to the unimaginably cosmic. Thank you so much for joining me on this explainer, and remember to always keep questioning the universe around you.